to asking what kind of mathematical structure does a theory have to have in order that the equivalence principle be true? What are the kinds of mathematics that have to describe it? I'm sure most of you know that general relativity is a theory not only about gravity, but it's a theory about geometry. So it's kind of interesting to start at the beginning and ask, what is it that led the man to say that gravity has something to do with geometry? Okay, so gravity equals acceleration. What does that mean? And I'm going to take you back. We're going to go through a very elementary derivation of what that means. It's not that this derivation is important, but it's worth formalizing. Formalizing means making equations that say the words. You all know that if you're in an accelerated frame of reference, an elevator accelerating upward or downward, you feel an effective gravitational field. Children know that because they feel it. You know that. You can probably even explain to me why that's true, but it's worth making a little bit of, it's sort of overkill, but making mathematics out of it, and then seeing what that mathematics is talking about. Okay, so let's imagine the Einstein thought experiment. Somebody in an elevator. The elevator got promoted to a rocket ship in later textbooks, but I've never been in a rocket ship, I've never been in an elevator, and so I know what it feels like to be in an elevator. And let's think of an elevator. An elevator is moving upward. It may be moving downward, in which case this velocity vector here is negative, but let's draw just a velocity vector. This is not a cable pulling it up, although it could be a cable pulling it up, but it's just a velocity vector. Okay, the velocity vector is up, and there are two coordinate frames. One coordinate frame is at rest on the Earth, and let's call it Z. I use the Z coordinate as a vertical coordinate of space, and down here someplace is Z equals 0. Could be the surface of the Earth, doesn't matter. Now, in the elevator, there's also a coordinate system, and that coordinate system is being measured. This is arbitrary, but we'll do it anyway. It's being measured from the floor of the elevator, and so the same physical point, let's say it's a point over here, has a Z coordinate, and it has a Z prime coordinate, and Z prime is measured from the floor. Now, the height of the floor of the elevator, the floor of the elevator, its height relative to Z equals 0, let's give a name, let's call it L. And L is clearly a function of time. We're going to be interested in the following question. If we know the laws of physics in the frame Z, surely we can figure out them in the frame Z prime. And we're going to do that. Now, one warning, not warning, but one fact about today's lecture. At least in the start, I'm going to ignore special relativity. This is tantamount to saying that we're pretending that the speed of light is infinite, or we're talking about motions which are so slow that the speed of light can be regarded as infinitely fast. In fact, you might say, if general relativity is the generalization of special relativity, how did Einstein get away with starting thinking without special relativity? And the answer is something like this. Special relativity has to do with very high velocity. Gravity has to do with heavy masses. There's a range of situations where gravity is important, where high velocities are not. So Einstein started out thinking about gravity for slow velocities, and then combined it with special relativity to think about the combination of fast velocities and gravity. And that's the general theory. But let's see what we know just from slow velocities. Okay. Let's begin with inertial reference frames. Let's suppose that Z prime, both Z and Z prime, are inertial reference frames. That means they're related by uniform velocity. Uniform velocity. And that means that L of t can just be taken to be Vt. the height of the elevator relative to the floor, relative to the, not the floor, but the relative to the ground, is just given by a uniform velocity v times t. I've chosen the coordinates such that at t equals 0, they line up. At t equals 0, both z and z prime are equal to 0. And now the elevator is rising, and the height is proportional. The height of the floor is proportional to vt. And then we can write down what the connection between z prime and z is. Z prime, this distance, is just z minus L. Now L is a function of time. So it's z minus L of t. If we know what L of t is, this is a kind of coordinate transformation. What about t prime? What about time in the elevator? We also ought to ask how time behaves in the elevator. If we're going to forget special relativity, then we can just say t prime and t are the same thing. We don't have to think about Lorentz transformations and that sort of thing. So the other half of the coordinate transformation would be t prime is equal to t, same thing. And finally, we could also put another coordinate in here. Later on, we'll be interested in the coordinate x going this way. There's also one coming out of the blackboard, y. And as long as the elevator is not sliding horizontally, then x prime and x can be taken to be the same. It's true, I've sort of offset the elevator relative to this axis, but I didn't have to do that. I could have put the z-axis right down the middle here, in which case I would say that x prime is the same as x. That's a coordinate transformation. It's a coordinate transformation of the space-time coordinates. It's rather trivial. Only one coordinate, namely z, is involved in any interesting way. We can, if we like, put a prime here because t prime and t are the same thing. Okay, now, if I set L of t equal to vt, then this is very simple, minus vt. Good. Now let's ask about a law of physics. Let's take the law of physics, Newton's law of motion, F equals ma. And what is A? A is z double dot. The second time derivative of z with respect to time. That's called the acceleration, the vertical acceleration. This, of course, is the z component of force. Let's forget about the x component of force and the y component of force. They're not interesting in this context. Whatever force is exerted, now this is the formula in the z frame. This is z. We can imagine in the z frame that there are forces acting on a particle. This could be a particle over here. There are forces acting on it. What do those forces do? Due to? Well, there could be some charge in here exerting forces on a charged object in here. It could just be a force due to a rope hanging the particle from the ceiling. Any number of different kinds of forces could be acting on the particle over here. And we know that its equation of motion in the original frame of reference is just F equals mz double dot. What is the equation of motion in the primed frame? Well, this is very easy. All we have to do is figure out what the original acceleration is in terms of the primed acceleration. What is the primed acceleration? The primed acceleration is obviously z prime double dot. And z prime double dot, z prime acceleration, is just gotten by differentiating this twice. But if I differentiate vt twice, I get nothing. Linear in t, differentiate it twice, you get nothing, and you simply find z double prime, z prime double dot is the z double dot. The acceleration in the two frames of reference are the same. Now, I know you know this. I know you know all about this, but I wanted to, sort of formalize it to bring out some points, in particular, the point that we're doing a coordinate transformation, and we're asking how laws of physics change in going from one frame to another. So now, what can we say about the Newton's law in the primed frame of reference? Well, we can now just substitute. F equals mz double dot prime. And what do we find? We find that the law, Newton's law, in the primed frame is exactly the same as Newton's law in the unprimed frame. That's not surprising. They're moving with uniform velocity relative to each other. If one of them is an inertial frame, the other is an inertial frame. Newton taught us that the laws of physics are the same in all inertial frames. So that's a sort of formalization of the argument. Now let's go to an accelerated reference frame. An accelerated reference frame, L of t will be increasing in an accelerated way. And so an accelerated way would be to put here 1/2 the acceleration times t squared, excuse me, and let's call the acceleration g, little g, for obvious reasons. Okay, let's call the acceleration little g. If you don't know what the obvious reason is, you'll find out in a minute. All right, now this is a uniform acceleration. If I differentiate L twice, the first time, let's do it. If I differentiate it once, I get L dot, and that's just gt.